Welcome everyone to the third day of the JMAC user conference and our second session of the day. My name is Anwu and I'm here to present our next speaker from Graz, Austria, Dr. Stefan Leitner. I will show him my screen. Okay. So Dr. Stefan Leitner is going to present today single-phase BLDC claw pole motor design, improvement and analysis. Dr. Stefan Leitner received his bachelor, diploma, and doctor in electrical engineering from the Graz University of Technology in 2014, 2016, and 2020. So congratulations again. That's very fresh. He's currently working as a postdoctoral researcher in the Christian Doppler Laboratory for brushless drives for pump and fan applications at the Electrical Drives and Machines Institute in Graz University of Technology. He has spent an academic year at the University of Tennessee, Knoxville, and he was a visiting scholar with Washington State University. His research interests include the design of fractional horsepower electric machines, and Mr. Leitner is a recipient of the Marshall Plan Scholarship, and he has received the Österreich Energy Prize in 2017 for his master thesis. He currently serves as the vice chair of the IEE chapter in Austria section. Please welcome Dr. Stefan Leitner. So, Mr. Leitner has prepared a presentation for us, and I will share it. Sorry. Now we'll share it. Okay.
Hi everyone, my name is Stefan Leitner. I'm a postdoc at the Christian Doppler Laboratory for brushless drives for pump and fan applications at Graz University of Technology in Austria, where we focus on the improvement of low power brushless DC motor drives for automotive auxiliary drive applications. I've been using JMAC for almost 4 years, mainly for the electromagnetic simulation of small electric motors, and today I'd like to give suggests. I will be talking about single-phase BLDC claw pole motor design improvements and analysis. One of the designs is actually shown here in this picture on the right. Well, I'm sure that at least some of you have already tried to slowly spin the shaft of a small PM motor by hand in the no-load condition. And what you feel is the cogging torque, which tries to restore the rotor to positions of minimum reluctance. Cogging torque can be a source of airborne and especially structure-borne noise in electric machines because, as it is superposed upon the alignment torque, it can trigger resonances of the drive system or adjacent structures. And today I will show you some interesting ways to reduce the cogging torque of small PM motors as opposed to conventional techniques with no increase to the manufacturing cost, which is super important for mass production. So after a short introduction, I will walk you through 4 different brushless DC claw pole motor designs, namely air gap asymmetry, single-sided skew with auxiliary slots, and V-skew, which I will explain later in more detail. They have been investigated with JMAC and also verified by different experiments, notably with a rheometer shown on the right, to cope with the very small torques. Rheometers are typically used in the chemical industry to study the viscoelastic behavior of, for example, ketchup or toothpaste. Then I will explain the used rheometer-based measuring techniques.
I'm very sorry. It seems as the picture is not very clear. I will try to rerun the presentation. Just a minute. Yes, I think this is better.
Which are used to experimentally determine the cogging torque, the hysteresis torque, and the iron losses of the manufactured prototypes, as shown here. And lastly, I will conclude the main findings. Introduction. Let's start with some background information. So when it comes to cars, there's two trends. Cars are becoming more and more quiet, especially when you think of electric vehicles, and the number of auxiliary drives is increasing, mostly for comfort and safety reasons. As a result, the noise of auxiliary drives is often unmasked, as shown in this picture, and can become disturbing. Hence, it is important to improve the noise behavior of these auxiliary drives. Currently, there's up to 100 small electric drives in a mid-size executive car, typical applications being illustrated in this picture. And one example I'm focusing on is the LED headlight fan for cooling and dehumidification. So what's the motivation? Auxiliary drives are typically characterized by suboptimal motor behavior for cost reasons. That means they are often single-phase instead of three-phase systems, so they are characterized by fluctuating power and torque. And due to the very low number of stator slots, these motors typically have a very high cogging torque, which can be a source of airborne and especially structure-borne noise. But what is cogging torque actually? Put simply, cogging torque is a no-load torque caused by the permanent magnets on the rotor, which aim to align with the maximum amount of iron material, minimizing the reluctance. So technically speaking, it occurs whenever magnetic co-energy changes with the rotor position. So the cogging torque is inherently offset-free. When the rotor is released from the shown position, the cogging torque will cause a counterclockwise rotation, trying to minimize the reluctance. A typical cogging torque waveform is shown in the picture on the right, with the cogging positions at 0, 90, 180 degrees, and so on. But there's both stable and unstable points of equilibrium. And in the end, the cogging torque is always superposed upon the alignment torque, increasing the torque ripple. But unfortunately, cogging torque reduction is typically expensive as additional manufacturing steps are involved, which is often a disqualifier for mass production. So the target is to reduce the cogging torque with no increase to the manufacturing cost through proper design modifications. And even though it's hardly possible, it's still important to note that a complete cogging torque elimination in single-phase motors can be detrimental as to the starting of the motor, but there's also different ways to deal with that. This slide should illustrate why, in my opinion, single-phase machines are much more fun than three-phase machines. As you all know, three-phase machines are characterized by a low output torque ripple, like shown in this plot, which results in a smooth operation. But in the amusement park of electric machines, a ride on a three-phase machine is more like the ride on a piggy parade. On the other hand, single-phase machines are more like the crazy roller coaster in the amusement park of electric machines. Much more fun, but as you can see, they can sometimes be too noisy. And that's why my target is to mitigate the high harmonics of the roller coaster a little bit by reducing the cogging torque and torque ripple and thereby potential noise. Let's move on with the studied motor topology. Here we can see an exploded JMAC model of the baseline single-phase BLDC claw pull motor. It consists of an outer rotor with permanent magnets, actually a permanent magnet ring, and a bifilar ring winding housed between two specially shaped stator parts, which are punched and subsequently deep-drawn steel sheets. As the two subfaces of the winding are wound simultaneously, they are very well coupled, as indicated in the electrical equivalent circuit on the right. Advantages is the fact that in this case only two MOSFETs are necessary for phase current commutation, using the signal of one Hall sensor. And for startup, this motor can be implemented, for example, with an asymmetric air gap, the design of which will be discussed shortly. Now I'd like to talk about the following four motor designs. While air gap asymmetry, design 0, enables the starting of the motor, design 1, single-sided skew, and design 3, single-sided skew and auxiliary slots, can reduce the cogging torque and hence the torque ripple through the...
Sorry, the video's not good anymore. I will do it again. So,
different skewing measures. Design 4, with its V-skew on the other hand, can reduce the cogging torque and at the same time balance the axial magnetic forces typically introduced by a single-sided skew. This effect is well known from skewed induction machines. Air gap asymmetry. In general, single-phase motors cannot start autonomously owing to their essentially alternating stator magnetic field. That's why many single-phase motors, single-phase BLDC motors, are implemented with an asymmetric air gap, in which the air gap length steadily increases along one stator pole. Thereby, the cogging torque, shown on the left, is altered, and shifted parking positions are created, from which the motor can start. So as you can see, the parking position is not at 90 degrees, for example, but it's a little higher. However, increasing air gap asymmetry causes the effective air gap to increase as well, which causes the air gap flux density and as a result the back EMF to decrease. So from this point of view, the degree of asymmetry should be kept as low as possible. Single-sided skew. So when you think of cogging torque reduction, what first comes to mind, of course, is skewing. But the big advantage of the claw pull motor topology is the fact that, thanks to the proposed punching layout, skewed stator claws can be implemented at the stage of punching the steel sheets at no increase to the manufacturing cost. So compared to conventional rotor or stator skewing, no additional manufacturing steps are necessary, which is a big plus. Now, implementing a skewing angle of 30 degrees can successfully reduce the...
we have the same missed low quality. I'm very sorry. I think it will keep continuing and I have to do it again. So.
Cogging torque by 23% in the simulations and by 28% in the measurements. As we will see on the next slide, a 30-degree skewing angle is chosen as a trade-off between maximum cogging torque reduction and minimum back EMF reduction. As can be seen, the simulation and measurement results agree generally very well. One interesting aspect though is the circled plateau indicated in red. In the simulations, it appears at minus 0.2 millinewton meters, while in the measurements it is shifted down to about minus 0.4 millinewton meters. So it looks like the waveforms are simply offset. As discussed later on in the section about rheometer-based measurements, this can be attributed to the hysteresis torque phenomena, which was observed only in the measurements because a detailed hysteresis loop model was not available for the used iron materials. So let's see what happens to the back EMF. The implemented single-sided skew of 30 degrees affects the back EMF only marginally. It is reduced by 1.7% in the simulations and by 1.9% in the experiments. As can be seen, the simulation and measurement results are in pretty good agreement. At this point, I'd like to make a comment on the used JMAC settings. The ring magnet was modeled having a radial magnetization pattern with 4 poles. To consider the pole transition zone of the magnet, a decaying was specified, as shown here, with rising and falling angles. So having performed the measurements, I had to play a little with this decaying angle. In this rather simple modeling approach, the magnetization is assumed to be trapezoidal. But if you want to go for full accuracy, JMAC offers the use of customized magnetization patterns. And last year we had a master student using this feature of JMAC. Therefore, he measured the magnetic field of a certain magnet ring utilizing a Hall sensor. Then he modeled the test setup as shown here and adapted the magnetization profile as shown here by trial and error, such that the simulated and the measured flux densities matched. Back to the different designs. In design 3, a single-sided skew is combined with auxiliary slots for cogging torque reduction. The introduction of auxiliary slots in design 2 can modulate the cogging torque as discussed in more detail on the next slide, and thereby making skewing much more effective in reducing the cogging torque. And again, this can be considered at the stage of punching basically for free. Let's take a closer look how this works. Every cogging torque waveform can be described by a Fourier series without the zero component. Introducing auxiliary slots, an additional cogging torque waveform is created, which is phase shifted from the initial one. And these two are then superposed. For the 4 stator slots and 1 auxiliary slot per claw pole, this superposition looks like this. But as you can see here, if the auxiliary slots are identical with the actual slots, the odd order harmonic components cancel out due to a 180 degrees phase shift, while the even order harmonics add up. And the result is shown in the plot on the right, where the new cogging torque has double the frequency. Now, as a second step, a single-sided skew is applied to the stator claws, which acts as an averaging filter. Therefore, the black waveform can be described by a new Fourier series. And solving the integral yields this equation. And for a skewing angle of 45 degrees and a slot number of now 8, the cogging torque is theoretically 0. In the implemented model though, this is not really the case, but it's largely reduced, which we can discuss later on. But let's take a closer look at the analysis results. Here we can see a comparison between the simulated cogging torque we saw on the previous slide and the measured cogging torque. Compared to the baseline in yellow, The cogging torque of the design 2, shown in black, is modulated due to the auxiliary slots, as expected, and then successfully reduced by 70% in design 3, shown in red, owing to a single-sided skew of 45 degrees. As can be seen, the simulation and measurement results agree very well. One interesting aspect, though, is again the torque offset observed in the measurements. Please keep that in mind for later. So in the end, this cogging torque reduction results in a torque ripple reduction of 17%, like illustrated in the simulation results here of the output torque, comparing the yellow and the red waveforms. On the downside, in design 3, the back EMF is reduced by 12%, which eventually results in a reduction in the efficiency of 3 percentage points from 36% to 33%. And having studied these designs electromagnetically, I was wondering if their thermal behaviors will be any different since the stator cooling surfaces are changed. So I decided to do a thermal analysis as well. Since I already had the models in JMAC, I did a thermal finite element analysis. And I also performed measurements in a climate chamber, shown on the right. In both cases, different input losses are dissipated in the winding, studying the steady state and transient over temperatures of the winding for different ambient temperatures. From the steady state analysis, we can obtain the overall thermal resistance, and from the transient analysis, we can calculate the thermal capacitance based on the thermal time constant measured. Exemplarily, here we can see the rise of the winding temperature of the baseline, showing the expected exponential behavior until a steady state is reached. The right plot shows the steady state winding temperature for increasing input losses for ambient temperatures of 30 and 60 degrees Celsius. As can be seen, the winding temperature increases linearly with increasing losses. The other two designs show very similar results with an about 7% higher winding temperature. The determined equivalent thermal resistances are all around 40 Kelvin per watt. It can be concluded that the proposed cogging torque reduction measures do not cause excessive heating. Back to the motor designs. One disadvantage of the single-sided skew is the introduction of axial magnetic forces. As you can see from this equation, the axial forces are proportional to the tangential forces, and they in fact increase with increasing skewing angle. So for a skewing angle of 45 degrees, the axial forces are even equal to the tangential forces, because the tangent of 45 degrees is 1. In the end, the fluctuating output torque of this motor will cause fluctuating axial forces, which can also lead to noise. And to balance these axial forces and still reduce the cogging torque, the design 4 is implemented with a V-skew, where positive and negative skewing angles are realized halfway through the axial length of the motor. Again, all can be included in the punching layout. And if necessary, you can also include some auxiliary slots of the same shape. This slide shows selected analysis results of design 4 with the V-skew in the no-load condition. Axial forces on the left and cogging torque on the right. Let's take a look at the axial forces first. Compared to the baseline, shown in black, the single-sided skew in design 1 introduces axial forces, as shown with the red waveform. But owing to the V-skew in design 4, these axial forces are balanced again. On the right, we can see the cogging torque of these designs, and most importantly, for a V-skew of 45 degrees, see the dashed gray line, the cogging torque of the baseline in black can be successfully reduced by 50%, while the back EMF is only marginally reduced by 1%. Rheometer-based measuring techniques. Measuring torques in the sub-millinewton meter range is challenging because especially friction can significantly affect the results. That is why I used a rheometer to determine the cogging torque, the hysteresis torque, and the iron losses of these small motors. The test setup is shown on the left, in which a clamping element attaches the rotor cup to the rotating shaft of the rheometer, and the stator is mounted onto the stationary lower part. For the measurements, the rotor is pulled over the stator and then rotated by the rheometer, measuring the torque necessary to perform the rotation. The general motion equation of this setup is depicted below, including the torque components to be expected, namely acceleration torque, the torque measured by the rheometer, friction torque, cogging torque, hysteresis torque, and eddy current torque. And by setting a constant rotational speed, the first term vanishes. And since the rheometer features radial and axial air bearings, and since there's no connection between the rotor and the stator, the friction term can be neglected as well. Performing the measurements at very low speed, for example 1 RPM, eddy current effects can be neglected as well. And this leaves us with this equation, which shows that the measured torque under these conditions is a superposition of the cogging torque and the hysteresis torque. And here we can see the no-load torque waveforms measured in the clockwise, black, and counterclockwise, yellow directions. Since the cogging torque is inherently offset-free, as we learned earlier, the observed offset is attributed to the hysteresis torque. So next I will show you how to separate them. Based on the previously determined torque waveforms for the clockwise and counterclockwise directions, the cogging torque shown in yellow can be determined by calculating pointwise the arithmetic average. Similarly, the hysteresis torque can be determined by subtraction, according to this equation. It is shown in red for both measuring directions in the plot. As can be seen, the hysteresis torque is far from being constant. In fact, it strongly depends on the rotor position, and this is caused by the stator slots. The average hysteresis torque of this claw-pull motor is higher than a comparable brushless DC motor with a lamination stack, because the claw-pull motor is made from cheaper iron material with a relatively large hysteresis area. For comparison, the measured cogging torque is contrasted with the simulated cogging torque, showing excellent agreement. Now we see that the plateaus of the two waveforms actually match. So we've seen in the previous slides that there's an offset in the measured torque waveform, which is attributed to the hysteresis torque. Now, performing measurements at elevated speeds, it is observed that this offset increases linearly with increasing speed. But as the hysteresis torque is essentially speed invariant, this increase is solely due to eddy current effects. And multiplying the measured offset torque by the angular frequency, the iron losses can be obtained and also separated, as shown on the right. Advantages is the fact that, as opposed to the investigation of sheet material properties, all manufacturing influences which typically alter the iron losses significantly are included in the measurements as the assembled motor is studied. That brings me to the end of this presentation. So I've mentioned that single-phase BLDC motors are characterized by high cogging torque and torque ripple, the harmonics of which can trigger system resonances and cause airborne or structure-borne noise. But unfortunately, cogging torque reduction is typically costly, so it involves additional manufacturing steps, which is often a disqualifier for mass production. However, in the proposed BLDC Kloppel motor designs, the cogging torque can be reduced and the axial forces can be balanced, both at no increase to the manufacturing cost, as the improvements can be considered at the stage of punching the steel sheets. In addition, I've presented a rather unconventional way to study the small cogging torque, hysteresis torque, and iron losses of these motors using a rheometer. With the rheometer, it was finally possible to have a detailed comparison between the cogging torque simulations performed with JMAC and the actual cogging torque of the prototypes. The references used throughout this presentation are provided on this slide. And one last thing, there might be no free lunch, but there's definitely free cogging torque reduction.
So again, very sorry for the technical issues. It seems somehow Zoom was downgrading all the quality of the video. But here with me is Dr. Leitner. Also to you, very sorry. It was a very interesting presentation, and I will make sure that the presentation is online for rewatching.
Yeah, sorry guys, next time I'm gonna do it live for sure.
So now we are having the question section. If you guys have any questions, please put it into the chat or in Vova, and Dr. Leitner is going to answer them. So far, we haven't received any questions, but we will. Oh, there's one. What was the calculation time, Mr. Leitner?
Okay, for the no load condition, it was about, I'd say 10 hours. And for the load condition simulations, about 24 hours. So it's a very detailed 3D model of the motor.
Okay.
So the mesh is very fine. I used 5 layers in the air gap. The trapezoidal, what's the name? Like triangles in 2D, and it's trapezoids in 3D, I guess.
Okay. So any more questions?
So I didn't use an extruded mesh, if that was your question.
Okay. We have no more questions. Oh, yes, we have another questions. Okay. So it's answered. Do you have experience with other cogging torque measurement setups?
Yes, we've tried it, but we didn't have the right sensors, and it's very hard to get good sensors to measure cogging torques that are so low. So as you saw, my cogging torques were in the sub-millinewton meter range, and it's always difficult to have a test set up. You would need an air bearing, for example, to get rid of the friction, and it gets very complicated. And with such sensors, it's very hard to get them, and they're very easy to damage. So that's why we tried out this rheometer approach, where we had this device known from the chemical industry. So we just had to assemble the motor, and it was very easy to perform the test compared to having our own torque measurement bed.
Can you tell a bit more about the adjusting of the magnetization?
Can you repeat that?
Can you tell a bit more about the adjusting of the magnetization?
Oh, you mean the trapezoidal one, or the customized optimization, the customized magnetization?
The first one that you mentioned.
Okay. So actually, when I started studying these motors, I got some models for different motors of the same size, and I looked at the settings, and my former colleague used a very large angle, a decaying angle, and the back EMF then looked more like a sinusoidal waveform, but I knew I was expecting a more trapezoidal waveform, and then I tried to decrease it like very much, so you have almost a rectangular back EMF waveform. And when we performed the measurement, I increased and decreased this angle until the waveforms matched pretty well.
Next
So
question.
I think it's a very good JMAC feature to easily consider the magnet transition zone, and you can very quickly change it and redo the simulations and get good results.
Okay, to the next question. Did you use a symmetric mesh in order to reduce noise mesh? I think it's critical for cogging torque result.
Symmetric mesh, I'm not familiar with this term, but you mean that all the poles have the same mesh? Is that your question? That the mesh is the same for all the poles? Okay. Yes. No, actually, that's a very, very good point. What I did was I used, I'm not sure if I used 36 points on the circumference in the air gap or 72. So, but I'm still pretty fine with regards to the mesh. And I used 5 layers. So I think the cogging torque should be calculated pretty correct, I'd say. But I will definitely check. It's a very good point. Thank you.
Okay. Next question. Was the efficiency comparison simulated or measured, or both?
This one was just simulated. So just simulated. You know, the back EMF reduced, and I applied the same voltage in JMAC, and that's why the current increased and the efficiency decreased. But the average output torque was almost the same, and it was just simulated. But by now we have different prototypes implemented in real fans, because the results I showed you was not the whole motor. I just wanted to verify the cogging torque reduction with a very simple test setup. So yes, it was just simulated. But right now we have also some measurements, and it yeah, it was very good. So it was very close to the simulations. So I know that the efficiency is very low in these machines.
Okay, next question. Usually these motors do not operate in a continuous regime. Was the same overload factor used for the single phase motor?
Continuous regime, I'd say the motors are so small that if you run them for like 2 minutes, it's like a continuous regime, I'd say, because they heat up pretty quickly to their thermal steady state temperature. So they we didn't use any overload factors. So I would say it is continuous regime because the heat time constant is very low. If that answers your questions, I'm not sure.
Okay, no comment. Maybe we'll wait for that. So far, that was the last question that we have received, but we will wait 1 more minute. So everyone.
So if you have any questions, send me an email, please, if you re-watch the video or in any case.
Yes, please rewatch this awesome presentation. It was very interesting. Yes, it was very interesting. So, Dr. Leitner, thank you very much. Do we have any final comments that you want to tell to the viewers? Okay. No. All right, Dr. Leitner, thank you very much again, and sorry for the technical issues.
Yeah, thank you.
It was a pleasure having you and this interesting presentation. And if you guys have any more questions to Dr. Leitner, please send him an email. And for this afternoon or right now, we are going to have the first session of today. And I will share it with you shortly. Once again. So we are going to have the next session is Agile Electrical Machine Development for Electric and Hybrid Electric Aircraft from Sultan Nadul Bari from Rolls-Royce. So if you want to attend this session, please log out of this session and then join at 12. And if it doesn't show a video, just refresh the browser. And then we will have a break. And after the break, we have at 3 p.m. modeling analysis and design of homopolar machine for aerospace and transportation application from Giulia Simoni from the University of Pisa. So it's also very interesting. And after that, we also have at 4 p.m. another session that is from my colleague, Mr. Ahmed Shoaib. And again, thank you very much for joining into this session. And again, thank you, Dr. Leitner. And
thank you too.
Please rewatch the presentation. We will upload it pretty soon. And thank you very much. And I will close this setting. Bye.
See you. Bye.